This is a lecture for universal gravitation. It says, if I have seen further than others, it is by standing upon the shoulders of giants. That's that famous quote from Isaac Newton again. The goals for this lecture is that you understand the factors that affect gravitational force, and by how much. So if you double this, what happens to that? If you triple this, what happens to that? You should also be able to calculate mathematically for a missing variable using Newton's law of universal gravitation. And finally, you should be able to distinguish between Newton's law of universal gravitation as written and with Cavendish's correction. So we'll start off with goal 3, and that is this. You see up top, you see Newton's version of Nlug, or Newton's law of universal gravitation. What that says is that the weight is proportional to mass 1, mass 2 over distance squared. And what this just means is, as this goes up by an equal amount. If this goes up by 4, this goes up by 4. And so they knew that there was this relationship between these three variables, but there was no sort of equality. One, because they didn't really have a unit for force at the time, but there was a missing corrective value. And Cavendish's correction is the version that we're actually going to use in this class. Now, it's still called Newton's law of universal gravitation because he was the one who made the giant leap in saying that this was correct. Cavendish's correction is this G term right here. This G term stands for the universal gravitational constant, and it should not be confused with our lowercase g value, which is the gravity of Earth. The lowercase g value, which is the gravity of Earth, is 9.8. This g term right here is 6.67 times 10 to the minus 11th. Okay, and you're going to see it quite a bit in some of the examples. So you don't need to commit it to memory because it will be on your formula chart, but you do need to know how to use it. Alright, this example says the gravitational force between two people is F when separated by a distance of D. If that distance is quadrupled, what will the gravitational force be? So you have person A, you have person B, they are separated by a distance of D, and they have a gravitational force of F. So if you were to quadruple that distance such that these people are much further away, you want to know what impact that has on the force. Now you should realize right away that when you get further away, the gravitational force is going to decrease. But the question is by how much? And that's where Newton's law of universal gravitation comes into play. We would say F equals G m1 m2 over d squared. So at this point, you want to say, okay, well, what impact is the distance going to have? And a lot of people get confused. They don't know what to do with the masses and so forth. But if you look, the mass of the people is going to be the same in each case. So what I'm going to do is I'm actually going to cross that out. And that's gone. And basically what that leaves me with is the proportionality where F is really proportional to d, 1 over d squared. So if I have 1 over d, like I did here, that gave me a value of F. So what I'm going to do is now, instead of plugging in D here, I'm going to plug in 4D. And when I do that, you get F is proportional, and then we do 1 over 4D, and then that whole thing is squared. And that's the key thing here, is this is an inverse square relation. So when you do this, you actually end up getting 1 over 16D squared. Remember, when we had 1 over d squared, we got F. So I have 1 over d squared here. The difference is I have F, and then I have over 16. So if I quadruple the distance, the gravitational force actually reduces to 1/16 as much, because it's an inverse square law. If I were to double the distance, the gravitational force would go down by 4, and so forth. You always have to square that number when it deals with distance. In this question, it says the gravitational force between a comet and the sun is F. So you have the sun and you have a comet, and they have a force of F. Now, it says as the comet reduces the distance to half. So now the comet is here, and the distance is d over 2. Or here, the distance was d. So now, but here's the problem. As the comet moves closer to the sun, it's actually going to lose its mass because it's going to start to melt. So mass decreases to 1/3 of its value. So here I had a mass of m. Here I'm going to have a mass of m/3. So I want to see what the overall effect of the gravitational force is. And so in order to do that, we say F equals g m1 m2 over d squared. When I do this, I have the mass of the sun, the mass of the comet, and the original distance between them. They give me a force of F. But now let's look at the second situation. I'm still going to have g. That's the universal gravitation that's not going to change. I have the mass of the sun. That is also not going to change. But now instead of m2, what I'm going to have is m2 over 3. And that's because the mass of the comet is being reduced. When I do it this way, the distance is also reduced. So instead of writing d, I write d over 2 and then square it. So at this point, what I want to do is I want to get back to this original equation. So I still have gm1 m2. So I'm going to go ahead and move this 3 down to the bottom where it belongs. And then when I square this, I'll show you what happens when we square it. We have g m1 m2 over, I'm going to put the 3 out here because I wanted to move that to the bottom. And then I'm going to have d squared over 4. Now when you divide by something that has a denominator, that can actually flip up to the top. So what that leaves me with is 4g m1 m2 over 3d squared. Now remember, g m1 m2 over d squared, that right there is F. So the end result is that the answer is going to be 4/3 F. So as I reduce the distance between them, the gravitational force is going to go up by a factor of 4. But because I'm reducing the mass of the comet, it's going to make it go down by a factor of 3. So the overall effect is that the gravitational force is pretty close to the same, although it does go up by a small factor. Okay, and this question says, what is the relationship between mass and the gravitational force? So we graph these all the same way. We're just going to sketch them. So we're looking at mass and its effect on gravitational force. So mass is going to go on the bottom and force is going to go on the y because we're saying that gravitational force depends on the mass. So once we've identified those, we look at our equation. The equation is F equals g m1 m2 over d squared. In this case, we're looking at just a single mass. So we're going to say mass number 1. We could say mass number 2 just as easily. When you're graphing these, you take the two things that you're graphing. In my case, force and mass 1. Everything else goes away. That goes away. That goes away. That goes away. Because they are assumed to be held constant. If you're increasing one variable, you want to keep everything else the same. So what that simplifies to is just F equals m. Okay, you should be able to recognize this relationship right away, but if you can't, remember F is on the y-axis, m is on the x-axis. So once you get it to this, you should recognize that, but if you don't, you generally have a graphing calculator. So you can say y equals x, and you can graph it. And as a result, you see the graph that's there, and it's a straight line up. So the relationship between mass 1 and force is a linear relationship. Alright, this example says determine the gravitational force between the Earth and the Sun when separated by 1.5 times 10 to the 11th meters. Now these are the values for the mass of the Sun, the Earth and the Sun, so we should be able to figure out what the actual gravitational force between the two is. So we are looking for Fg. Now since I'm looking for the gravitational force and I have two masses separated by a distance, I know that Fg equals mg will not work. Instead I'm going to have to say, well, the gravitational force is equal to G, which is the universal gravitational constant, m1, m2 over d squared. So now we can get our given information. We were given the mass of the Earth. I'll call that m1. The mass of the Sun. And we were given the distance between the two. Now, so if we were to draw this out, we would see you have the Sun, which is very, very large, and the Earth, which is much, much smaller, and there's a distance of 1.5 times 10 to the 11th in between them. You should realize that they are both attracted to each other with the same gravitational force, which is what we're trying to calculate. Now, the effect on the Earth is going to be much, much larger because the Earth is very, very small compared to the Sun. So, before we move on, a lot of people might be hung up on why I decided to make the Earth mass 1 and the Sun mass 2. It actually makes no difference. If you look at the formula, you're going to multiply the two together anyway. So just as a simple example, if I take 5 and multiply it by 4, I get the same thing as if I take 4 and multiply by 5. So don't be caught up in terms of what's supposed to be M1 and what's supposed to be M2. You can just assign them however you're more comfortable with. So now, we can plug in our values. Remember, G is a constant. We can always find it on the star reference chart, or we can just say that it's 6.67 times 10 to the minus 11th multiplied by 5.98 times 10 to the 24th times 1.99 times 10 to the 30th, and all of that is divided by 1.5 times 10 to the 11th, and that is squared. So if you can't tell already, it is very, very important for these questions that you actually be able to solve or be able to enter these exponents into the calculator well. Now, for some reason, because people see times 10, they automatically try and do that in the calculator. Please don't do that. If you have a calculator, what you want to do is you want to use the exponent button, which on the TI graphing calculator is the double E button, which is just above the 7. So I would enter that as 6.67 second comma, which gives me that E, negative 11 times 5.98 E24 times 1.99 E30, and now I can take that whole thing and I can divide it by 1.5 E11 squared. When you do that, you get a value of 3.53 times 10 to the 22nd newtons, which is a very, very large value. But it's something that we should expect. I mean, if we're looking at what is keeping the Earth moving in a circle around the Sun, we would expect it to be a very, very large value. And it is. Okay, in this example we have two metal spheres that are 1 kilogram each, and we have a force between them that we measure. We want to know the distance between the spheres. So this is just a variation of the Cavendish experiment where we're actually trying to solve for distance instead of actually having distance already. So let's look at this and we say, okay, we are trying to solve for the distance, or the d. We know that we are going to use Newton's law of universal gravitation. And we can go ahead and draw it out. You have a 1 kilogram object. You have another 1 kilogram object. You know the attractive force, and you want to figure out what the distance is between them. So let's look and see if we can figure this out. So our given information, you know that mass 1 is 1 kilogram. You know that mass 2 is 1 kilogram. You know that the force between them is 1 times 10 to the minus 5th. And then you always know that G is a constant. So when we look at this, we can say Fg is equal to capital G, M1, M2 over D squared. Remember, this G is just defining this as the gravitational force. It's not 9.8 there. Remember, it's a little subscript. It should be maybe a little smaller like that, Fg. So I'm going to rearrange and I'm going to solve for D. How I'm going to do that is I'm going to basically switch this term and this term, multiply both sides by D squared, Divide both sides by F, and when you do that, you get D squared equals G M1 M2 over F little g. So now, in order to figure out what this is, I would take the square root of both sides, and that would give me my D value. So now, the square root of 6.67 times 10 to the minus 11th times 1 divided by 1 times 10 to the minus 5th, and that would allow me to figure out my distance. So I'd say 6.67 e minus 11 times 1 divided by 1 e negative 5. Now this is the value that's all of these numbers right here. So at this point, what I need to do is I need to take the square root of it. So I take the square root at the end, and when I do that, I get a value of 0.0026 meters, which is about 2.6 millimeters as far as the distance between them, which is not entirely possible because this is actually the center to center distance. And assuming that the spheres have any sort of shape at all, it's going to be almost impossible for that to occur. So you're looking at very, very, very small forces for gravity for everyday objects. The only time you get large values is when you talk about things that are like planets and stars and so forth. Alright, this is the final example for this section. It says an asteroid of unknown mass approaches Earth. And we have the mass of Earth that's given to us. It says it is determined that the gravitational attraction between the two is 18,000 newtons when separated by 1 times 10 to the 8th meters. And it says what is the mass of the unknown asteroid? So this is one of the ways they can measure the mass of things that are far away, because obviously you can't put them directly on a scale, but you can measure their attraction or their interaction with other objects. There's a little bit easier way that we'll show you a little bit later, but for now, let's go ahead and take a look at this. It says, okay, I want to know mass. I'm going to say that's mass 2. I know that I'm given information that I can make Newton's law of universal gravitation work. So here's the Earth. Here's the comet. I'm going to assume the comet is smaller, but you never know. There is an attractive force, because gravity is always attractive, of 18,000 newtons. And you know that they are separated. Okay, this distance is the center to center distance of 1 times 10 to the 8th meters. So let's take a look at this. We can write our given information out. We can say Fg is 18,000. We can say that the mass of object 1 is the mass of Earth, which is 5.98 times 10 to the 24th. You can say that the distance between them is 1 times 10 to the 8th. Okay, and then you can say we are trying to solve for mass 2. So now I'm going to take this equation, I'm going to rearrange it. You have Fg equals G M1 M2 over D squared. To isolate M2, what I have to do is the opposite of what I have here. So I'm going to multiply both sides by D squared. That'll cancel out with that. Divide both sides by G over M1. When I do this to both sides, what I get is F D squared over G M1 is equal to M2. So now that I have it in the form that I want it to, I can say, okay, that equals 18,000 times 1 times 10 to the 8th divided by 6.67 times 10 to the minus 11th times 5.98 times 10 to the 24th. Okay, because of the way that we have it set up here, you're going to have to be very careful with your parentheses, because this whole term, when you divide, needs to be in parentheses. So we'll show you what that looks like in the calculator. So 18,000 times 1e8 divided by parentheses 6.67 e minus 11 times 5.98 E24. And when you do that, you get a mass, a very, very, very small mass, you get a very, very small mass of 0.0026 kilograms. Alright, so now that we've worked through all the examples, you should see what I mean by understand the factors that affect the gravitational force. So what effect does doubling distance have on the gravitational force? Well, it reduces it to a fourth of its value because distance is a squared term. You should also realize that when you double the mass, you double the weight or the gravitational force as well. So increasing the mass increases the weight or force. Increasing the distance between them actually decreases the force. You should also be able to calculate for an unknown variable using Newton's law of universal gravitation as shown in the many examples in this lecture. Also, you should know how to distinguish between Newton's version and Cavendish's version, even though they are both called Newton's law of universal gravitation.